So, from last time, we were talking about the complex numbers, and we talked about division of complex numbers, where we are dividing a fully complex number by an imaginary number. So, what we had said was we can think about this as the division of each of these things individually. Now this second piece, the 2i over 3i, the i's can just cancel. Our issue, though, is on this first fraction, because this is not a complex number. The reason it's not a complex number is because the I is in the denominator. We need to figure out a way to move that I from the denominator to the numerator. So the way to do that is going to be simple. We can just multiply this fraction by I over I. Why is that going to work? Let's see what happens. So we're going to end up with 6i in the numerator, and then 3i squared in the denominator. And I'm still going to have that 2/3 there at the end. But what does I squared equal? Is there any way to remember? So if we go all the way back, we remember that we said I squared was -1. So I can just replace that with -1. And then similarly, the 3 and the 6 can reduce. And we're left with, I'm going to write this in the opposite order. I'm going to write the 2/3 first, and then minus 2i. Madison? Mm-hmm. I don't even know what letter we're on. I'm going to just start with E. It's probably not the right letter, but okay. What if we do this problem where we have two fully complex numbers that we're going to divide? Well, in a similar fashion, I'm going to set this up as a fraction, where I'm going to have dividend divided by or over top of my divisor. Now, what I'm going to do here, again, I want to accomplish the same goal, where my issue is I have this I in the denominator that I need to take care of. And I'm going to do a similar trick where I'm going to multiply the top and bottom of this fraction by something to get rid of the I in my denominator. What do you think that something's going to be in this case? So this is a little bit more difficult situation. Is I going to do it? It's not. The reason is that when if I were to multiply I to the denominator, it would have to distribute to both pieces. So I'd end up with a 5i, which doesn't get the I out of the denominator. What I'm going to multiply these by is 5 minus 2i. Notice here that what I've chosen is the same thing as the denominator, just with the opposite sign in between the real and imaginary parts there. So now I'm going to FOIL things out. 2 times 5 is 10. 2 times negative 2i is negative 4i. Negative 3 times 5, or negative 3i times 5 is negative 15i. And then negative 3i times negative 2i is positive 6i squared. And I'll do the same thing down here. 5 times 5 is 25. 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. And then 2i times negative 2i is negative 4i squared. So notice all I did there was a bunch of FOILing, right? And what is I squared equal to again? That's negative 1. So when I combine like terms in the numerator, I have 10 plus 6 times negative 1, which is just 4. And then I have 4i minus, or negative 4i minus 15i, which is just negative 19i. In the denominator, I have 25 minus 4 times negative 1. That's just going to be 29. And then negative 10i plus 10i gives me 0. So I'm not going to bother to write the plus 0 there. So my last step then is to just write this as a complex number. So I'll write that as 4 over 29 minus 19 over 29i. Questions about that? Okay. Well, this was the last set of topics that I wanted to talk about before the end of inside of chapter 3. So let's take a moment here and just kind of recap what we've done inside of chapter 3 here. So the first thing we did was talk about graphing. We talked about how to graph in 3 different forms. We talked about graphing when things were in vertex form. In order to graph any quadratic, I needed to find the vertex. So we had a different way to find the vertex regardless of which form we were in. So vertex form, intercept form, and then standard form. remember what this f of notation meant is you just, like f of p plus q over 2 just means you take your answer for p plus q over 2 and plug that in for x in our original equation. So graphing was one big skill that we talked about a lot. For simplifying, we talked about first how to convert between these three forms. Converting between vertex form, standard form, and then intercept form. To go from vertex form to standard form, we expand. To go from standard form to intercept form, we factor. To go from intercept form back to standard form, we FOILed. And to go from standard form to vertex form, we did completing the square. The other simplifying topic we've talked about is the one we just finished, which is just operations on complex numbers. So that's add, subtract, multiply, and divide. Are the four operations on complex numbers that we talked about. And then the final skill that we were responsible for was solving. And we talked about three different ways to solve. We talked about solving by factoring. We talked about solving directly. Where we just use like a square root to do it. And then we talked about, bless you, using the quadratic formula. So that's basically chapter 3 as a whole. So I know chapter 3 spanned quite a few days. We did a lot of things there, and we had a lot of practice, but the summary took 5 minutes or so once we've kind of clear about what all these little things were. My plan here for today is to just talk some more about, now that we've kind of outlined what we did in chapter 3, to talk some more about individual topics that we've just got done kind of outlining that you guys feel that you would like a little bit of extra review with. So I'm just going to do some problems or some examples and just walk through any of these little areas that you guys feel like that you'd like to see a little bit of extra review on. Okay? Justin? Sure. So let's say we want to graph 2x squared minus 12x plus 5. First thing I'd want to do is identify what form that I'm working in. Is this vertex form, intercept form, or standard form? It's a standard form. Okay. So for standard form, I know that I can calculate the x-coordinate of the vertex by doing negative b over 2a. So in this problem, what are my values for a, b, and c? What's a? 2. And what's B? Negative 12. And what's C? 5. Everybody's okay there? So when I plug in here, I have negative of negative 12 over 2 times 2. That simplifies down to positive 3. The y-coordinate then is just f of negative b over 2a. So that's f of negative 3. And what f of negative 3 means is that everywhere there's an x in my original equation, I'm just going to replace that x with a negative 3. Not negative 3. I don't know why I wrote negative. It's definitely a positive 3. How come you guys weren't yelling at me for that? Okay. So 2 times 3 squared is 18. Minus 12 times 3 is 36. 18 minus 36 is negative 18. And then plus 5 more is negative 13. Those are the same. Yep. Those are just the same. So what we have then is our vertex is the point 3 comma negative 13. Justin, so far so good? Okay. Now I'm going to make my 5-point table. I like to draw mine horizontally, because the middle point in my table is going to be my vertex. And then I'm free to choose x's kind of as I see fit. I should pick 2 x's that are less than the x-coordinate of my vertex, and then 2 x's that are bigger than the x-coordinate of my vertex. So what 2 x's do you want to pick on the left here? Okay. And then on the right? Good. Those are the ones that I would choose. I just picked the whole number values closest to your vertex. So now to find these y-coordinates, we're going to find those the same way we found the y-coordinate of the vertex. So for 1, I'm just going to plug 1 in for x. When I do that, I get 2 minus 12 is negative 10, plus 5 is negative 5. And then I'll plug in 2 for x. See, 8 minus 24 is negative 16, and then plus 5 is negative 11. And now I could keep doing the same process, but there's also a shortcut. What is the shortcut here? Does anyone remember? Good. That is the shortcut, is that these values should match up, provided that the pattern of increase in the x is the same. So notice how we're just going up by 1s for the x's. That tells me that my table will be symmetric like that the y's will match up. So now all I'm left to do is plot some points. And let's see, 1, negative 5. 2, negative 11, 6, 7, 8, 9, 10, 11, 3, negative 13, 4, negative 11. Oops, forgot to put a 5 out there. I'll do that right now. And there's that. Stop it. All right. So there's my points all plotted. Now I just need to connect them. What is this shape called of the graph that I just drew? Yeah, it's called a parabola. Probably not as lumpy as mine looks there, but I guess it's not that bad. Justin, does that feel okay? Yeah. And so you can graph any quadratic function in kind of in the same fashion. What's the only part of this is going to change depending on the function? It's how you found your vertex, right? Depending on what form it's in, you'd use a different formula to find your vertex. But everything else should stay the same. Justin? I'm sorry, Juan? Sure. You want to talk about one of these simplifying problems then? Before we move on to that, is everybody happy with graphing? Well, we'll see how much time we have. That's why I'm asking you guys for what you want to do. I'd like to be able to go slowly in detail rather than try to do everything. Okay. Oops. So let's say we wanted to convert y equals x squared plus 4x minus 7 to vertex form. What form is x squared plus 4x minus 7 in? This is standard form, right? So if I go back to my table, I'm in standard form, and I want to go to vertex form. So to do that, I have to do completing the square. Everybody agree with that? Okay. So the first step is to make that leading coefficient equal 1. What is the leading coefficient in my problem? It's already 1, so I don't have anything to do there, okay? Next step would be to move the c, or the constant term, to the other side. So to do that, I'll just add 7 to both sides. The next step is to add b over 2 squared to both sides. What's my value for b here? It's 4. So on the left-hand side, I'm going to go ahead and simplify that b over 2 squared. So b over 2 is 4, and 4 squared is 16. Sorry, b over 2 is 2, and 2 squared is 4. Jeepers creepers. And on the right-hand side, I'm not going to do the squaring, but I notice I can simplify 4 over 2. So I'll go ahead and do that. over 2 squared is 4. My next step would be then to factor that right-hand side. So I just abbreviated right-hand side as RHS. So I know this is going to factor in a very predictable way. And then I'm going to go ahead and add the 4 and 7 there to make 11. So the first thing here is going to come from the first squared part. So that's just going to be an x. The second thing is going to come from the second squared part. That's going to be the 2. Okay there? And then the last step is to just get that y by itself. For this problem, I just need to subtract 11 over and I'm done. Zach? Why don't I just take that out? X plus 2 squared is x plus 2 times x plus 2, right? So when I FOIL that out, I get the 4x is still there, right? So I did account for the 4x, it just didn't happen to matter in the type of factoring that I'm doing, because this factoring is like taking advantage of a very special factoring pattern where I don't really need to know what that middle thing is, that middle part is doing in order to factor it. Is that okay? Yeah, so it's still there. We did account for it, didn't go anywhere. It just didn't happen to affect how we did our factoring. Juan, did that feel okay for the completing the square part? This piece? Because to factor it, I really wanted to know what I squared. So it just made it easier for me to do the factoring, to leave it as something squared. And that's the only reason. It was just to make the factoring a little bit easier to deal with. I could have just as easily written it as 4, but then that makes the factoring a little bit harder by doing too much simplifying there. So that's the only reason. Does that satisfy you? Okay. Tommy?
In the equation, it says that f equals a times x minus h squared plus k. Where's the a? Oh, it's 1. Oh.
Okay. Madison? If you wrote it as 4 over 2 instead of 2? Yeah, if it's a reducible fraction, I'd prefer that you reduce it. So like 4 over 2 is obviously just 2. It's not wrong if you write it as 4 over 2 because it's still the same thing. It's just not very standard. And I'd prefer if you had a reduced fraction, but if it was like 7/3 or something, just leave it as 7/3. If it doesn't reduce, don't monkey around with it. Just leave it as an improper fraction or whatever. Does that feel okay? Okay. Okay. Caden, you said you want to do another one of these or 2 of these or whatever? Sure. Okay. Let's say I asked you to convert y equals negative 2x plus 3 squared minus 6 to standard form. First thing we'd want to do is identify what situation we're currently in. So if I look at that, what form is that in? If I go back and I look at my list, it looks like vertex form to me, right? So we're starting in vertex form, and we want to land in standard form. So to do that, I need to expand. Is everybody okay with how I use that chart? Oops. Okay. So when we say expand, what that really means is we just need to multiply that x plus 3 squared out. I know something squared is really just like that thing times itself. So what I'm going to do is I'm just going to start by foiling. And then I have some like terms that I can combine inside that parenthesis. 3x plus 3x is 6x. And now I can distribute the negative 2 through. So negative 2x squared minus 12x minus 18. And then I still have that minus 6 at the end. And then negative 18 minus 6 is negative 24. And I'm now in standard form, and I'm finished. It's not so bad. Questions on what I did there? Tommy?
No, wait,
Okay. Sophia?
So is the expanding just kind of like the distributive property?
It's kind of just like a FOIL and then a distribute. It's kind of what you're doing there. And then there's some extra combining of like terms at the end, but that's basically what we're doing.
Okay.
The reason it gets a more generic term is that, like, you know, we might be interested in things like this, which there's a better way to do this other than foiling 4 times, which is what you'd have to do to multiply that out. And we'll talk about that a little bit later, maybe second semester, probably. But we give this a special name. Now, in the case of where the exponent is 2 like this, expanding and foiling, there's not a whole lot of difference. But there is a shortcut way around having to do the foiling. But in the case of this, it's not any shorter. Is that okay? Okay. Nancy? Of course. Okay, and you feel happy on that? Okay. Tommy?
You want to use that,
Sure. So, first thing I'll do is figure out what form I'm in to start with. That is standard form. So if I go back to my chart, oops, let me just do this. To go from standard form to intercept form, we have to factor. So to factor this, I need to find 2 numbers that multiply to give me A times C. So that's going to be 2. And then add to give me b, so that's going to be 3. The two numbers that do that are 2 and 1. So what I use those two numbers for then is I'm going to take my original problem. I'm going to use those two numbers to break up that middle value. So instead of writing it as 3x, I'm going to write it as 2x plus 1x. I'm going to make my two groups. Now I didn't have to worry about anything here because there's already a plus sign in between those two groups. If I happen to have a subtraction symbol, all I do is write it as plus a negative, and the negative goes inside of the one group. But I should always have a plus sign in between the two groups. From the first group, I'm going to look for a greatest common factor. I notice that each of them has a 2x in it. So when I factor that 2x out, I get x plus 1. Everybody okay there? Remember, when I'm factoring out, I'm dividing. So 2x squared divided by 2x is just x, and 2x divided by 2x is just 1. If I look at the second group, what can I take out of those? Just a 1, right? When I take that out, does anything happen? No. Everybody so far so good? Yeah, Caden? Because when you do 1 divided by 1, you get 1. Remember, when we're factoring out, we're dividing. Now, if I look at each of these, I notice that I have something in common. What's in common? X plus 1. And what's left over then, when I factor those out, is the 2x plus 1. Now, we're not quite done, because they're not actually in intercept form. Let's hold on, can you hold on for 1 second? Why aren't we in intercept form? Let's go look at what intercept form says again. Well, we have an A. The A is 1, right? The bigger issue is the coefficients on our x's have to be 1. Notice that our coefficients on our x's, one of them is 1. The other one, though, is 2. So we do have a little bit of rearranging to do to get to that intercept form. But we're very, very close. And the fix is not difficult, but I wanted to make sure that we're clear as to why we're not quite in intercept form yet. Everybody's okay still? Juan, your question is? Okay. If it comes back to you, let me know, and we'll certainly come back and address it. I was just kind of in the middle of a thought, and I didn't want to pause there. Okay. So this is my issue, right? Is this 2x here needs to just be a regular x. Everybody's okay with that? So here's the fix. All I'm going to do is factor out a 2. So 2x divided by 2 is x. 1 divided by 2 is 1/2. And because this is just 3 things multiplied together, I can write those in any order I want, and I'm done. Tommy? Sure. Were we okay with why I took the 2 out, everyone? So Tommy just wanted an aside factoring using the shortcut. I just wanted to factor x squared plus 9x plus 18. All I need here is the two numbers that multiply to give me 18 and add to give me 9. What would those two numbers be? 6 and 3. So I can go with those numbers straight to my answer. Those should be easy to do. Those ones that are just times table kind of problems, right? How did you come up with 6 and 3 so quickly? You just thought about the things that multiplied to give him 18, and then found the pair that added to give him 9. Always start with the multiplication problem, and just using your times tables, basically. You remember those things that you had to memorize in elementary school that none of you thought were important to memorize? Ha ha ha! They're back. Okay. What next? So we've done some simplifying problems, we've done some graphing problems. What else did you still want to talk about that was on our list there? Happy to do as much as you guys want, like anything you guys want to talk about, this is the time to do it. It's been a long time that we've been kind of picking away at chapter 3, so I want to make sure that we have a chance to recap things that might have been from distant past. Kaden, did you have your hand up? No? All right. Justin? You mean the complex numbers? Okay. Okay, so those are, yeah, yeah. So if I want to add two complex numbers that look like this, all I'm going to do is add the real parts together. So 7 plus negative 2 is 5. And then I'm going to add the imaginary parts together. Negative 3i plus 6i is positive 3i. And I'm done. If this was, say, a subtraction problem, what I'd want to do is I'd want to distribute the negative to turn it into an addition problem. So when I distribute the negative 2 becomes positive 2, and the positive 6 becomes negative 6. But then if I combine the real parts together, I get 9. And when I combine the imaginary parts together, I get negative 9i. Does that feel okay there, Justin?
Yeah.
So it works kind of in the best case scenario, right, where we're basically just combining like terms. Kaden? Those are two separate examples. So this is like example A and this is example B.
Yeah, I know, but like when you
Which negative sign are you talking about? This one? So if I look at negative 3i and negative 6i and I'm adding those together, I get negative 9i. And then adding a negative is the same as subtraction, right? Is that did it? Okay. Yeah, you can just distribute the negatives and turn it into an addition problem. It's probably the easiest way to handle that. Ty? Of course. Yeah. Could be, sure. Do you want to talk about that some?
Mr. Lewis, why would it be seven? Never mind. Yeah, never mind.
So let's do a division here. So what if we wanted to divide these two complex numbers? We said that we're going to write these like a fraction. And the issue here is that I have an I in the denominator of this fraction. If I can get rid of all the i's in the denominator, we're in good shape. So to get rid of the i's in the denominator, I'm going to multiply the numerator and denominator of this fraction by some complex number. The complex number I'm going to use is going to be based on the denominator, and it's going to be the same thing, just with the opposite sign in the middle. Every time. And now we just need to multiply out the numerator and denominator, and everything should kind of fall into place for us. So to multiply these out, I have to FOIL. So 7 times negative 2 is negative 14. 7 times negative 6i is negative 42i. Negative 3i times negative 2 is positive 6i. And negative 3i times negative 6i is positive 18i squared. If I do the same thing here, negative 2 times negative 2 is 4. Negative 2 times negative 6i is positive 12i. Positive 6i times negative 2 is negative 12i. And positive 6i times negative 6i is negative 36i squared. Addison? Why? Can you repeat that? I'm sorry. Right, so why would I be doing it to the, what is negative 2 minus 6i over negative 2 minus 6i? That's just 1, right? And I can always multiply a number by 1 and not change the value of it at all. So that's why it has to be the same thing on top and bottom. And the reason I only flipped the 1 sign in the middle, you're going to see in just a moment when we simplify the denominator. The goal is to get the i's out of the denominator. And let's look at what happens here when we actually finish up simplifying in the denominator. Okay? So I notice that, or I know I squared is negative 1. So in the denominator, I have 4 minus 36 times negative 1. Well, that's just going to come out to be 40. And then I have a positive 12i and a negative 12i. Those added up to give me 0. And I have no i's in my denominator. That's the point. So Madison, if I had made also the 2 positive, the i's in the middle wouldn't have canceled out. So that's the reason why we're only changing that middle number sign, is if I change anything else, the i's won't cancel out. So you're not going to get this part to happen, which is what we want to have happen. We want to get rid of all the i's in the denominator. Is that? Okay. Yes, sir. Yes, so negative 1 times negative 36 is positive 36, and then plus 4 is 40. Yes. We'll do the same thing here in the numerator. So again, I squared is -1, which makes that a -18. And -14 and -18 is -32. And then -42i plus 6i is -36i. And now I'm just going to write this as a complex number. That's going to be 32 over 40 plus 36 over 40i. But look at those fractions that we have there. Do you notice anything about those? They can reduce, yeah. So -32 over 40 becomes -4/5. And 36 over 40 becomes 9 over 10. Zach? So remember, a complex number should be of the form a plus bi. And if we divide two complex numbers, we need to get another complex number back at the end. So I need something that's written as a plus bi, which is not how this is written. So the last parts there is just for style, to make sure that I've written my answer as a complex number. Is that okay there? Okay. Nancy.
Why is it -32 plus 36i if 36 is negative?
Oops, you're right. Thank you. So that should be a subtraction symbol. That should be subtraction. And that should be subtraction. Thank you. Yes, you're absolutely right. Didn't appreciably change anything else afterwards, but yeah, that sign matters. Yes, that should have been negative. Thank you. It was a lucky mistake and I didn't have a lot to fix. Joan. Of course. Do we feel a bit better about the divisions here? So it's not too bad, right? The process is kind of the same every single time. Hopefully we understand why we're choosing what we're choosing to multiply the top and the bottom by now. And everything should work out to where you have no i's left in your denominator. That's the goal. Okay? I think the only thing left to talk about is solving. Should we talk about some solving stuff? Might as well. Okay. So we had talked about there being 3 different solving methods that we might use. Factoring, solving directly, and the quadratic formula. Which of these is going to be the fastest or easiest method to go about this one? Because that's how we really want to be doing these solving problems, right? We don't want to be doing them necessarily all the same way. We'd rather do them like the easiest route possible. I would do this directly. Why would I want to do this one directly? Just kind of using like the reverse order of operations is what I mean by directly. The reason I would do that way is because all I have is an x squared. Notice that there's not also x's. Do you guys see that? Okay? So to do this, I'm just going to get the x's on one side and everything else on the other. Negative 36. And then we'll divide both sides by 4. And then we'll square root both sides. What do I have to remember when I square root both sides of an equation? Plus or minus. Not enough of you guys said that. That makes me a little nervous. And then how do I deal with this square root of a negative 9? When I square root a negative, what do I get? I get an I. And the square root of 9 then is just 3. So what we're doing here is we're just really rewriting the square root of negative 9 as the square root of negative 1 times the square root of 9. The definition of I is it's the square root of negative 1. Right? That's how we defined I. So this would be our answer. Let's do another one of these, yeah? Sure. So how about this one? Okay, you want to get everything onto one side. Sure. Okay. And as long as we're doing that, what else should we do? X squared, you mean? Okay. So when I do that, I get x squared minus 3x equals 0. Okay. How do I want to handle that? How do I want to solve that? Dude, factor is. How does this factor? Just take out an x. Right? Everybody agree with that? Then I can apply the zero product property and set each of the two things equal to 0. That's already solved for me. There's my answer, 0 and 3. We'll pause here.